Now we're going to apply what we learned previously. So those concepts, we're going to apply it in this problem. And in class tomorrow, on Wednesday, we will go over some workout problems related to these concepts. So that's why I'm solving this problem, because this is kind of the basic understanding of the concepts, and we'll do this together in the videos. So again, this is a point charge in an electric field, and a charged ink drop. The mass is given, the charge is given in an inkjet printer, initially moves along x-axis with a speed of 18 meters per second between two charge plates. The plates create a uniform E field of 1.4 times 10 to the 6 newtons per coulomb. If the plates are 1.6 centimeters long, what is the vertical deflection of the ink drop at the end? So that L is given. And now we're going to apply the homework layout. And this is all about Millikan's oil drop experiment. Okay, so this you're going to see kind of how he calculated the this, like, the vertical deflection in this case. So the given is, we have the mass, so we write mass 1.3 times 10 to the negative 10 kilograms. Q is negative 1.5 times 10 to the negative 13 coulomb. And what else do we have? We have the speed, and it says along the x direction, so let's say Vx, 18 meters per second. And we have the electric field, not just itself, but in vector form, because we see the direction here as well. It's negative 1.4 times 10 to the 6 newtons per coulomb, J hat, because it's downward along y-axis, and the L, the length, 1.6 times 10 to the negative 2 meters. So these are the values that we have, and we are trying to find the vertical length, get the deflection. So it started from this point, it ended up this point, so we are really finding this height here. Let's call it y, so we are trying to solve for y. Okay, so this is the setup. The figure is here. We already discussed a few things here, right? The force direction, acceleration direction. We already know that the force and acceleration are upward. And you know that, again, it says here, the speed is to the right. It came with a speed, but then in the electric field region, it deflected because of that electrostatic force pushing this charge upward. And that force is accelerating the object upward as well. So the only acceleration we have here is along positive y direction. Okay, so we're going to put those together to figure out this position. And just like we wrote down in the first slide, the steps, like F is equal to QE, F is equal to MA, and then once you know A, then you can solve for positions as well, right? So that's kind of the steps that we're going to do. And I'm going to continue the rest of it right here, not that one. Let's create a new one. Okay, so we have the given, find, and figure. Let's continue with assume. And here we will have, we know that it is uniform E field. Oops, get rid of everything. Uniform E field. And it is isolated system. That means we don't worry about gravity, okay? So we're just going to say no gravity, ignore it. And for the plan, let's say we will apply F is equal to QE, right? And then second law, so F is equal to MA. And then constant acceleration equation. So could be x equals to x0 plus v0 xt plus 1 half a xt squared, and y is equal to y0 plus v0 yt plus 1 half a yt squared. So those are the plans. Now you can see that it's almost a mechanics problem. The only difference is we just are starting with an electrostatic relation. So the solution, let's put it over here. Okay, so we know that force is created by the electric field, right? So we need to think about how to get the force. Again, F is equal to QE. Since they used capital Q for the charge, I'm gonna replace it to that. And the value was negative 1.5 times 10 to the negative 13 coulomb. That is the charge. And the electric field in vector form, negative 1.4 times 10 to the 6 newtons per coulomb J hat. And that gives us the force direction. Two negatives multiplied, we get positive. That's why it is opposite direction to the electric field. Because force is positive, electric field is negative direction. And 2.1 times 10 to the negative 7 newtons. So that is the force. And that's the electrostatic force. And next step is F is equal to ma. And again, this is the sum of forces. And the only force we have is this force, the electrostatic force. So the sum of forces is really F. And that F is 2.1 times 10 to the negative 7 newtons, J hat direction. The mass was given as 1.3 times 10 to the negative 10 kilogram times A. Now we are solving for A, and from this relation A, we get positive 1.6. Since this is vector equation, since I'm using like all the vector notations on one side and the unit vectors on the other side, I'm getting the vector right away. And this is positive 1.6 times 10 to the 3 meters per second square. Again, J hat, they are consistent. So, and this is the acceleration. Again, we're trying to get to the position. So next is gonna be applying our step-by-step process. If you recall it from mechanics, we're trying to get y. And as a step one, we write down the equations, right? X equals to x0 plus v0 xt plus 1 half ax t squared. We also have y component. Y is equal to y0 plus v0y t plus 1 half ay t squared. Step 2 is at the start. What do we know? Do we know x0? Yes, we can take it as 0. Do we know y0? Yes, we can also take that as 0. We can start the charge at the origin as it's shown in the figure. And what else do we know? v0x, that is positive 18 meters per second as given. And you know that this is constant. And v0y, it doesn't have that, so it's simply 0. And at the end, we can think of what we have at the end. X is the length, right? So it's simply L. And the L value is, let me see, 1.6 times 10 to the negative 2 meters. That's where it gets in this, along the X direction. And Y is unknown, right? So it's simply Y, or you can just put a question mark. And we want Vx, let's write the X first. Vx is the same because it's not changing. So it's positive 18 meters per second. And Vy is unknown. And also we have, we don't really need those because we're not going to use the velocity equation, but still I want to think about it. In between those two, we have acceleration x. acceleration y, and the time. Okay, so ax is simply 0, right? Because the velocity is constant. You can see that v0x and vx are the same. And ay is, let's just see what we had. 1.6 times 10 to the 3, and this was along y direction, so that's what we're going to use. 1.6 times 10 to the 3 meters per second squared. And the time is unknown. Okay, so what we're going to do is then, let's find the time so we can solve for y, right? I'm going to go back to my equation and do some cancellation. So I'm going to say x0 is 0. Cancel that. Y0 is 0. Just cross it out. V0y is 0. That goes away as well. And what else? And ax is 0. So that's a good one. So those are going to go to 0, all those terms. And you can simply see that you have everything else except the final velocity along y direction. And we don't really need to use it anyway. So, but they could have asked about that as well. As you remember from mechanics, we had those problems a lot last semester. So here, what I need to do is then I need to use, let's call this one equation 1. And this one could be 2. From equation 1, I'm going to solve for time. So I'm just going to plug what I have. So that is x is equal to 1.6 times 10 to the negative 2 meters. That's equal to v0x is 18 meters per second, and t. So t from here is going to be, if you calculate that, you get 8.9 times 10 to the negative 4 seconds. And from equation number 2, we can solve for y component, y position actually. And I'm going to show like this. So y equals to, first two terms go away. It is 1/2 acceleration, ay, and we already know that it is 1.6 times 10 to the 3 meters per second squared. And the time square, so it's 8.9 times 10 to the negative 4 second squared. So when you put these together and then check the units as well, we will get meters. We should get the value to be 6.34 times 10 to the negative 4 meters. Excuse me. And y is equal to, if I write this in millimeters, it will be 0.634 millimeters. Okay, so I'm writing in millimeters because you can see that it's almost 1/2 millimeter. Think about how small it moves. And then, like, by changing the electric field, or varying the electric field, you can really move the inkjet, like ink, any position you want. And that's how they make those letters, A versus L, right? Like some of them, they just kind of position-wise, they change, and this is how they move things. So one more thing that we need to do is to think about reflection. So point charge was given a uniform field, right, in this problem. And so what we did was we used the electric field to find the force. So we really used F is equal to QE to find F using the given electric field. And then since Q was an electron, actually not just an electron, but a negative charge and bunch of like electrons, or I should probably just say negative charge. And because of that, electric field and force directions were opposite. And so like F and E points opposite directions. And then we use this relation. So since E was downward, we got F upward, right? And then because of F is equal to MA, we also found that A was upward as well. And that's because of the second law. Okay, mass is always positive. F and F and acceleration is always the same direction. I'm trying to fix that. It looks like a negative sign. It is not a negative sign, of course. And after that, since the force was constant, acceleration was constant, then we were able to use a constant acceleration equation, especially the position equations. Constant acceleration equations were valid. And that's how we figured out y. First we found the time from the x-axis, and then we solved for